Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 15, seminar 6, in which we will solve our next problem, number 16, the objective of which is to construct a circle that is orthogonal to two given fixed coplanar circles and that passes through a given fixed coplanar point. When we analyze the input material of this problem, then we realize that it is possible to partition all the possible mutual juxtapositions of the input objects in this problem into three distinct cases. In the first case that we will consider, the two input given fixed coplanar distinct circles have precisely 0 points in common. 0 points in common, and in this case there are two possibilities. Both circles are located one outside of the other, or one of the circles is properly contained within the other. For example, we have a bigger input circle and somewhere inside of it is a smaller circle, again honoring the constraint that these two circles have 0 points in common. In the second case that we will consider, the two given input fixed distinct coplanar circles have precisely 1 point in common. In this case, again, there are two possibilities. One circle can be touching the other one like so, with the so-called internal tangency, and in the other case we can have two circles touch each other externally like so, and in the third case the two input given fixed distinct coplanar circles have precisely and exactly 2 points in common, which means that these two circles intersect over two distinct points, and we will begin the analysis of the solution of this problem with the first case. When the two given fixed distinct coplanar circles have precisely 0 points in common, then there exist two scenarios of the mutual juxtaposition of these circles. The circles are located strictly one outside of the other, or one of the circles is contained by the other circle. For demonstration purposes, I will consider the first scenario when the circles are located strictly one outside of the other, and you are more than welcome to examine the remaining case, but there is no fundamental difference between these two scenarios. And in this case, the solution of this problem is very similar to the solution of the problem that we solved in the previous seminar, the solution of the problem number 15, with the minor exception that in the previous problem we reflected two distinct points in one and the same circle, but over here evidently we will be reflecting 1 point in two distinct circles. That is, let us assume that we're given an input circle lowercase q1 shown in white on the right side of your screen, and we're given the second fixed distinct circle from the circle q1 named q2 shown on the left side of your screen in white. Both of the circles are positioned in the same plane and they have precisely 0 points in common. One circle is located outside of the other outside of the one, and we're given a sample point P that is coplanar with these two input circles. Then, in order to construct a circle that passes through that point P and that is orthogonal to both input circles, the circle Q1 and the circle Q2, we already understand what needs to be done. I will not go into all the details of explaining why we do it. I will just say that first we reflect the point P in the circle Q1 with positive power once into its image point P1, shown over here in yellow. We know how to do that. That can be done with Euclidean tools alone with absolute certainty. With a compass and a straight edge, we know how to do that. There is nothing new over here. And once we do that, we will obtain the line segment P1, which we then bisect with the perpendicular bisector named B1. B1 shown in yellow. The angle technically over here is right. We depict the right angle with the square looking formation like so. And we know that perpendicular bisector B1 contains uncountably infinitely many points, each of which can play the role of the center of a circle that passes through the given point P and is orthogonal to the circle Q1. Likewise, as the second step, we reflect the point P in the circle Q2 with positive power once into the point P2 shown in light blue over here. That task is again completely doable with Euclidean tools alone. We know how to do that. Once we obtain the point P2, we construct the line segment P2, which we then bisect with the perpendicular bisector B2 shown in light blue. The angle over here technically is again right. We depict it with the squarey looking symbol, and we also know that that perpendicular bisector B2 contains uncountably infinitely many points, each of which can play the role of the center of a circle that passes through the point P, and that is orthogonal to the circle Q2. Consequently, using the method of intersecting loci, we claim that if the two perpendicular bisectors, the perpendicular bisector B1 shown in yellow and the perpendicular bisector B2 shown in light blue, intersect in the Euclidean plane, they will intersect over a unique point on only one point. We will name that point O, and that point O will be the center of the sought after circle that is orthogonal to two given input circles Q1 and Q2, which in this case have precisely 0 points in common, and the circle that passes precisely through the point P, because here the circle W, we name that red circle shown in the middle of your screen right here. That circle W will have that point O as its center, and it will have the radius, the length of the line segment OP. We claim that this circle will be orthogonal to the input circles Q1 and Q2, and it will pass evidently by the means of construction through the point P. And there is an implicit if statement over here. I will not be writing down the explicit algorithmic steps. You should do that on your own. You should also generate the proof that this algorithm that we just described does produce the circle, a unique circle that is orthogonal to the two input circles and passes through the point P. Do that on your own and analyze the case of what will happen if the perpendicular bisector B1 and B2 do not intersect. You already know from the analysis of the problem from the previous seminar. In this case, the perpendicular bisectors will be parallel, and if they are parallel, then that means that the center of the input circles, let's give them the name uppercase Q1, uppercase Q2, and in this case the centers of the input circles Q1, Q2, and the point P will be collinear. Then the perpendicular bisectors of the corresponding line segments will be parallel, and in that case, what will be the solution circle? Well, as we discussed in the previous seminar, in this case we will have a circle that passes through 3 such points and that has its center taken into the point at infinity, and evidently that will be a straight line that passes precisely through the centers of the input circles, the points uppercase Q1 and uppercase Q2, and the input point P. In order to demonstrate the technical essence of this algorithm visually, I have put together an animation for you using the free software called GeoGebra. And in that animation, in a few seconds, you will see two distinct and fixed input circles that have precisely 0 points in common and that are located strictly one outside of the other. You will also see the given point P that will roam the parent plane along a certain straight line. For simplicity, I hid that straight line, that orbit of the point P, in order to avoid the clutter. And as this animation progresses, I recommend that you pay attention not as much to the point P, but to the angles that are formed by the radii of the three circles at hand. In this animation, I constructed the circle that you will see in the middle over here precisely according to our algorithm. Reflect 1 point in the first circle with positive power ones, reflect the same point in the second circle with positive power exactly 1, bisect the corresponding line segments, obtain the point, and then draw that circle. And as the point P is animated, the solution circle W will move in a certain way. It will change its radius apparently, but the line segments that I drew from the centers of both circles to the points where the solution circle intersects these two circles, this point and this point, will be depicted with an angle, and you will see that the magnitude of this angle will have this squarey symbol attached to it, and this is a way for GeoGebra to show that the magnitude of this angle is precisely 90 degrees or pi over 2 radians. In the second case, the two fixed given distinct coplanar circles have precisely 1 point in common, and in this case there are also possible two scenarios for the mutual juxtaposition of the input circles when these circles touch each other externally or internally. Again, fundamentally, there is absolutely no essential technical differences between these two scenarios, and for demonstration purposes, I will consider the first scenario when the two circles touch each other externally, and for completeness, you are encouraged to consider the case when the two input circles touch each other internally yourself. To that end, we observe that we are given the input circle Q1 shown on the right side of your screen in white over here. This circle is slightly larger than the second coplanar given fixed distinct circle Q2 shown over here. This circle is shown in white on the left side of your screen. These two circles touch each other externally at the point shown in blue over here. I named that point T for tangency. And in this case, we have a fork. We consider first what will happen if the given point P is actually exactly the tangency point T. Well, in this case, the situation is not very interesting because right away we know that if we construct a common internal tangent, in this case, when the two circles touch each other externally, then the two external tangents degenerate or merge into one. I designated this one internal tangent with the lowercase tau, and it's shown in dashed line over here. This is the common internal tangent right here. Then that internal tangent tau will house uncountably infinitely many points, each of which will be the center of a circle that passes through this here point T, which is the point P, and is orthogonal to both input circles Q1 and Q2, there is zero intellectual voltage in generating these solutions. This is not very interesting, and we do not even need the theory of inversion of the real plane with respect to a circle in order to do that. So from now on, we will throw this case out, and we will consider the case when the point P through which the sought after circle that is orthogonal to two given circles that touch must pass, and that point is distinct, explicitly distinct from the single point that these two circles have in common, the point T. Let's say this point P is located over here. It doesn't really matter where it is located. Again, there are different positions. We consider the general one. On the one hand here, it seems that it may be possible to show that the solution circle W, that's the circle we're looking for, shown in pink color over here in the middle of your screen, passes through the point P, orthogonal to both input circles Q1 and Q2, can be constructed very, very quickly. Simply draw the line segment PT, bisected with the perpendicular bisector, and where the point where this perpendicular bisector intersects the common internal tangent tau marks the spot, and that point will be evidently equidistant from the points T and P. Snap a circle that has the center at that point and the radius. Let's say if we call this point O, OT, and OP, game over. It can probably be shown with the methods of elementary middle school plain Euclidean geometry that this will be the case, but because we're the students of the inversive geometry in this course, we want to concoct an elegant line of reasoning that is based precisely on the machinery of inversive geometry. We want to showcase our understanding of how these things work and how we solve problems using this machinery. If you missed our seminar number 1, we recommend that you find that seminar where I explain in detail how to apply the machinery of inversive geometry to the process of solving problems. Over here, I will skip that description altogether and I will cut to the chase. We will basically use the transform and conquer problem solving approach. And what do we see? Well, based on all the theorems that we proved, the moment we see that two circles touch, or two circles or some number of circles pass through a given point, we think, this may be a very good candidate. Remember that in problem solving, there are no guarantees of any kind, but this is definitely a good candidate to try for the center of inversion. As such, we claim that, shown in olive on the upper right side of your screen over here, the circle named lowercase c that has the center at the point T, the sole common point between two input circles, and it has for the radius the distance between the points T and P. I've shown this circle in dashed olive color. If you can see this greenish yellowish color, this is the circle of inversion, the center of inversion, and TP, this radius right here, this radius is the radius of inversion. So this is our winner. This is the idea that you were expected to generate if you want to get a solid A for the solution of this problem and show your knowledge and understanding of how inversive geometry works. Center T, the radius, the distance between the points TP, the power of inversion will always be positive, plus r squared. All the inversions will be carried out once. And why did we choose this specific center of inversion? Well, look at this. Based on the theorems that we proved earlier, any circle that passes through the center of inversion, which our circles, input circles Q1 and Q2 now certainly do, will be taken by the inversion with basically positive and negative power alike into what? Into certain straight lines. As such, we record this fact over here. The input circles, lowercase q, 1, 2, under the inversion of the parent plane with respect to the circle that is parameterized over here with positive power will be taken into its images q prime 1, 2. But these will be straight lines. The straight line q prime 1 shown over here on the right, q prime 1, and the straight line q prime 2 shown on your left. Now, the input circles are parallel. It may sound a little funky, but that is what it is. The input circles are parallel because the angle between the tangents drawn to these circles at the points of interest is exactly 0, or if we want to get more nuanced with the directions, plus minus pi, for example, but it doesn't matter. The tangents are parallel, the circles are parallel according to the corresponding theorem that we proved in one of our last lectures. We know that as a mapping of a, let's say, real or a complex plane into itself, inversion of the plane with respect to a circle is anti-conformal. It changes the directions or the orientation of the angles of all the relative angles to the opposite, but it preserves the magnitude. And that means that if the input objects or pre-images are parallel, then their images under the inversion, under the chosen inversion, will also be parallel, and that is what is reflected over here. Q prime 1 straight line is parallel to the straight line Q prime 2. Two distinct. The circles are distinct, the images are distinct, so it is important we have two distinct straight lines that are parallel to each other. And now we come to the technical essence of the transform and conquer. Where did we gain the competitive advantage by going through all this inversive magic? Well, we gained the competitive advantage over here by realizing that our inverted solution has the menu that is quite shallow. There are only two choices on this menu. The inverted solution can only be a circle or a straight line. This is it, because this is what we proved through the collection of all our theorems and problems that we solved. Circles go into circles or straight lines, and straight lines go into circles. So this is all our only choices. Now, we will use the so-called eliminate and conquer problem-solving approach. Again, the menu is shallow and it's not that deep, but nonetheless, technically, eliminate and conquer in action. We go through the list of suspects one by one, and we begin eliminating those that definitely cannot satisfy the solution, the requirement of the problem. Can a circle that passes through the point P be orthogonal simultaneously to two distinct parallel straight lines, Q prime 1 and Q prime 2? Well, in Euclidean geometry, this is absurd. This cannot ever happen. Why is that? Because a straight line is orthogonal to a given circle if and only if that straight line passes through the center of that circle. As such, assume we pick a circle that is centered on the straight line Q prime 1. That circle passes through the point P. Will that circle be orthogonal to the straight line Q prime 1? Sure, it will be. But that circle can never ever be orthogonal to the remaining straight line Q prime 2. And conversely, if we pick any point on the straight line Q prime 2, say over here, we construct a circle that passes through the point P, that circle will be orthogonal most definitely to the straight line Q prime 2, but it can never in Euclidean geometry be orthogonal to the straight line Q prime 1, and that violates our requirement. Remember, our circle, if it exists, has to be orthogonal simultaneously or at once to both of the geometric objects at hand, Q prime 1 and Q prime 2 straight lines, and it has to pass through the point P. So now we proved that this choice is impossible, no go. So the only suspect that's left is a straight line. And look at this. In Euclidean geometry, how many straight lines perpendicular to two distinct parallel straight lines and passing through a given point can be constructed? Only one. And that straight line is shown in the middle of your screen over here in pink. This is the inverted solution. It is important to understand that now we're deep in the bowels of transform and conquer. Remember, take the input material, transform it into a tactically advantageous setting, solve that problem there, easier problem there, and then reverse transform the solution of the transform problem into a solution of the original problem. So here, this is exactly where we gain the competitive advantage. With the Euclidean tools alone, a straight edge and a compass, we know with absolute certainty how to construct a straight line that is perpendicular or orthogonal, if you will, to two given parallel straight lines, which are distinct, Q prime 1 and Q prime 2, and passes through the point P. That can be done. This is a trivial task. We construct this straight line, and then look at this. the straight line W prime that is orthogonal to the images Q prime 1, 2, and it also contains or passes through the point P. This is exactly the point that is we need to deal with when we construct our solution circle. Now what? Well, the reverse transformation in this case is, again, the inversion of this whole plane that contains all this beautiful mess in the circle C, which we parameterized and defined over here in the circle C with positive power only once. And remember that we said that the point P specifically is distinct from the point T. And what is the point T in this case? The point T in this case is the center of inversion. Remember that we equipped our real plane with an extra point, the point at infinity, and we agreed that under any inversion, the center of inversion is taken into the point at infinity, and conversely, the point at infinity is taken into the center of inversion. But this time, the point P is distinct from the center of inversion. This is so-called finite point. No matter how far it is, that distance is still finite. The point P is not the point at infinity. So that means that the straight line shown over here, W prime, pink in color, will be taken into what? It will be taken into a circle. Remember our earlier theorems that passes precisely through the center of inversion. And that circle W shown over here in the center of your screen in pink will pass through the point T, but it will also pass through the point P, the given point P. Why is that? Well, remember that this was literally, I think, the very first theorem that we proved that under the inversion of the real plane with respect to a circle with positive power, the point, any point on the circle of inversion, and that is how we constructed our circle of inversion. It contains the point P. The point P sits precisely on that circle because that is the point that defines the radius of the circle. That point is fixed or stationary, it's taken into itself. Under the same inversion of the real plane with respect to a circle with negative power, that point will be taken to a diametrically opposite image. But our power inversion is positive. The point P remains where it was. It's fixed. That is why we have this beautiful arrangement of things where the point P is not going anywhere. And if the straight line passes through that point, then the circle will most definitely pass through that point itself. And voila, we have our solution, our algorithm. Now, this is the line of reasoning that justifies the construction of the sought after circle that is orthogonal to two given circles and passes through the point P. And I encourage all our viewers to convert that line of reasoning into a formal proof. I will skip that proof. Once you generate that proof, you will see that when it comes to the actual mechanics of the construction of the solution, we do not really need to invert all these objects. Let's say if we were played by the letter of the inversive geometry law, all we have to do is, what do we have to do? We have to draw the circle of inversion. That much we need to do. And then in that circle of inversion, we will reflect, let's say, one circle. It doesn't really matter which one. One circle is enough. Let's say we invert the circle Q1 or the circle Q2. All we're after is that straight line. Once we have that straight line, we snap a perpendicular to it through the point P. That's enough. And once we have that straight line, we invert it. We bend it into a circle through the same inversion with positive power in the chosen circle, and voila, we have our solution circle, a beautiful and elegant line of reasoning that is based precisely on the mechanics of the inversive geometry. And again, in a few seconds, you will see an animation that I have put together for you using the free software called GeoGebra in order to demonstrate the technical essence of this algorithm that we described. In that animation, again, I kept the input circles fixed. The point of tangency is fixed, but the point P, you will see, roams the parent plane in some interesting way. This is our secret, don't tell anyone. It runs its orbit is a straight line, which I hid in order to avoid the clutter. Again, the solution circle W that is orthogonal to two given input circles and passes through the point P will breathe. Somehow it will change, but I encourage you to pay attention to these points right here, because these points I connected with the centers of the input circles and the center of the solution circle. And GeoGebra, remember, shows any angle, usually with the circular arc, but when the angle is right, and it shows it with the squarey formation, it's very sensitive. So if you see this squarey formation as an angle designation, you know that the corresponding angle is right. Lastly, we consider the case when the two input circles have precisely two distinct points in common, which is to say that these two circles intersect over the points which, for definitiveness, we will name F1, F1, and F2, F2. Here it may seem that we may have somewhat two distinct scenarios when the smaller circle is located inside the larger circle in such a way that the circles intersect, or the smaller circle, let's say, is located outside the center of the circle, let's say outside the larger one. Again, there is absolutely no fundamental difference. Here, for demonstration purposes, I will take it that we are given an input circle named Q1 shown on the right side of your screen, partially over here. We do not really need the whole thing. This is the circle Q1, lowercase q1, and on your left side, we're given another input fixed coplanar distinct circle shown in white, Q2. These two circles intersect over two distinct points, the point F1 shown in, let's say, blue, and the point F2, also shown in blue, two distinct points. And here we seek an algorithm that involves precisely, or the reasoning behind that algorithm involves precisely the machinery of inversive geometry. And that target or sought after circle should be orthogonal to two circles shown over here, Q1 and Q2, and it should pass through a sample point, let's say P. Again, for the point P, we also have a multitude of positions. I will only consider the interesting case when the point P is located in such a way that it is not point F1 or F2, because in this case, let's say the point P, let's write it down over here. Let's say the point P is, so happens that it is point F1 or the point F2. Well, in this case, we have the situation when two circles in general are not orthogonal, so this doesn't really make any sense. This can only work when one of the circles degenerates into a point, precisely into that point, and then there is no interest in that problem because we snap a tangent to the given circle, whichever did not degenerate into a point or a circle with zero radius through that point, and then any circle that has the center on that tangent and passes through that point is orthogonal to the given circle and degenerate circle that became a point. So this is not interesting. So from now on, we take it that the point P is distinct, precisely distinct from the point F1 and F2. Let's say it so happened that the sample point is positioned over here. Again, we want to come up with an elegant line of reasoning that precisely rides the machinery of the I in here, inversive geometry of the real plane. So what can be done? Again, the moment we see two circles that intersect or pass through a point, or some number of circles pass through a given point, we already know that this is a good candidate to consider for the center of inversion. Here we have two choices. We can make the point F1 the center of inversion, or we can make the point F2 the center of inversion. Again, there is no material or fundamental difference. The technical essence of the idea that you were expected to generate over here is the following. Take one of these points as the center of inversion. We depicted this over here. Look at this. Again, in this olive color, I designated the circle of inversion lowercase c. That circle is shown partially in olive right here. and the lowercase letter c over here. Don't miss that one right here. So this is the circle, and it has the point F1 as the center. The point F1 as the center, and the distance between the distinct points. Remember, these points are distinct. This is the case that we are covering. We should probably also write the fact that, let's say we can write it here, that F1 is specifically not is equal to F2. This is our constraint. So this situation always makes sense. So we have a non-degenerate circle, and we put the compass, let's say the needle of the compass, into the point F1, and with the radius F1, F2, we snap our circle of inversion lowercase c. So this is a winner. What happens now? Remember that we described this technology in the seminar number 1. Now we invert all the local material in the chosen parameters of inversion and see what happens. Well, in this case, our input circles Q1, 2 inverted or reflected in the circle C, shown over here, with positive power 1s, into the images Q prime 1, 2. But this time, notice this, that our images will intersect, and this is the important part. This intersection symbol I underscored with the pink chalk just to emphasize the fact that they will intersect. We already also know the Euclidean tools only algorithm in favorable cases, how to construct these images. We know that, for example, let's say our circle of inversion intersects the first circle Q1 at another point somewhere here, and it intersects the second given input circle at some point over here. All we do is we snap two straight lines through the points that are common to the circle of inversion and the input circles, and game over. This is it. The images are complete. It's that simple. We proved the corresponding theorems in the course early. In other words, the circle Q1 is taken into the straight line Q prime 1. Look at this, Q prime 1. That straight line goes over here, and it passes through the point F2. And the circle Q2 is taken into the olive-colored straight line Q prime 2. Q prime 2 shown over here. These two straight lines intersect precisely at the point F2. This fact is depicted over here. Now what? Well, our straight lines, Q prime 1 and Q prime 2, represent the easier, in some sense. Again, this is another incarnation of the transform and conquer problem solving approach, whereby transforming the local material into a setting that is advantageous, this is how we gain the tactical advantage. So now we think, if we take our point P and flip it in the same circle of inversion with the same power, positive power, into the point P prime, let's say over here, the given point P shown in blue is taken into the point. Remember, these points have to be collinear with the center of inversion. This point was taken somewhere into P prime, doesn't really matter. But now the inverted solution, again, is represented by a menu of choices that is quite shallow. We don't have that many choices on our menu. The choice is, again, a circle or a straight line. And again, we engage into or bring in the eliminate and conquer problem solving approach. We begin eliminating the usual suspects until whatever remains, no matter how improbable, must be the truth. In our case, look at this. Our inverted solution object must be what? It must be orthogonal to two distinct intersecting straight lines, Q prime 1 and Q prime 2, and it must pass through the point P prime. From the menu of choices, what is possible and what is definitely not possible? Well, in Euclidean geometry, let's loiter around the straight line. Can we construct a straight line that is simultaneously orthogonal to two intersecting straight lines and that passes through a given point, P prime? No, it's not possible. It is only possible to construct one. For example, we can snap a perpendicular to the straight line Q prime 2 through P prime, like this, all day long. That is fine. And the image of that straight line will be orthogonal to the circle Q2, but we will leave the circle Q1 out in the cold. It will not be taken care of, because that perpendicular to the straight line Q prime 2 cannot possibly be perpendicular to the straight line Q prime 1, and conversely, all day long we can construct a straight line that is perpendicular to the straight line Q prime 1 and passes through the point P prime, but that straight line, that perpendicular, will never be orthogonal to the straight line Q prime 2. So the image of that straight line will be, again, something that will be orthogonal to the circle Q1, but the input circle Q2 will be left out in the code. So now we eliminate the straight line from our menu of choices. The only choice that's left is a circle. So the question now is, in Euclidean geometry, how many circles can be constructed if the center of that circle is given and it must pass through a particular point? Well, only one circle, and that is exactly what we do. We put the needle of our compass into the point F2. We now pay attention. If the center of inversion F1, our straight lines, the images of the input circles, will intersect at the point F2. So here we put the needle of the circle of the compass, and we open that compass up to cover the distance from the point F2 to the point P prime, which is the image of the point P under the inversion of the plane in the circle that was chosen over here. If we flip these points around, then we will go the other way. We'll draw the circle centered at F1. We snap the circle, here shown in dashed line called W prime, centered at the point F2, and the radius of that circle is shown as the distance between the points F2 and P prime. Pay attention over here and to understand what is going on. The radius of the circle is the distance between the point F2 and P prime. That circle shown in dashed, and that circle represents what? That circle represents, here what I wrote for the steps, construct the circle W centered at this point with that radius. We do that manually. We can do that with, evidently, just the Euclidean compass is enough. We construct it ourselves. This is our will. But that object represents the solution of the inverted problem. And how do we do the reverse transformation? Well, in this case, we again flip or reflect, if you will, the circle W prime that we just constructed in the circle C, with positive power once into the circle W that we claim will be orthogonal to the input circles Q1, 2, and it will also pass through the point P. In other words, the circle W thus constructed will be precisely a unique circle that is orthogonal to two given circles Q1 and Q2 that intersect over two distinct points, and that passes through the point P. I try to portray this circle for you over here with, again, with the pink color. It will be quite large. Again, it doesn't really matter. It has to pass through these points and this point, so it will go somehow like this. Again, here the visuals are not that important. It is important to understand the essence of our algorithm and of our reasoning. How did we generate that idea? You should be able to algorithmicize this solution on your own, generate a proof. Again, once we show all these steps, usually the analysis becomes basically or fundamentally becomes a proof. Once we write it up formally, it becomes a proof. And in this case, look at this. This circle will run like so. It will be perpendicular to both circles, and it will pass through the point P. Again, once you write your formal proof, you will have to say which words. You will have to say the words that the point P, technically in grown-up mathematics, we will call this point finite. In other words, this is not a point at infinity, and neither the point P prime. Remember, P, we specifically pick the point P distinct from either points where the circles intersect. It means that whichever point we pick for the center of inversion, the center of inversion goes into the point at infinity. Point at infinity comes back to the center of inversion. These points are neither. They're distinct. So all is good. And this guarantees that we will produce a correct solution. The circle W, constructed as follows, is the image of the circle W prime that has the point F2 as its center, and its radius, the distance between these points, and the image P prime of the point P under the inversion of the plane with positive power with respect to the circle C shown in olive that has the point F1 as the center and the distance F1, F2, this distance right here as its radius. Problem solved. And again, in order to demonstrate the technical lessons of this algorithm visually, I have put together for you an animation using the free software called GeoGebra. Again, in this animation that you will see in a few seconds, I have the input circles fixed, the distinct points over which these two circles intersect fixed, but the point P will roam the plane in some secret orbit. Don't tell anyone this is a straight line. I do not show that straight line to avoid the clutter, but pay attention again. As the point P roams the parent plane, look for the angle between the radii of the circles Q1 and Q2 that I construct to the points that are obtained by intersecting the solution circle, and the radius that is drawn from the center of the solution circle again to these points where these input circles intersect. This is it for this seminar. We are done with the problem number 16. If you have any questions, by all means do ask. The comment section is open, but perhaps if you have a question before you ask it, I recommend that you click on the link again under this episode and open the corresponding chapter of my free book, Inverse Geometry for All, on which this seminar and this entire course is based, and see if you can figure things out by reading my printed material. If not, then of course by all means do ask. And as a fair warning, as a heads up, in the next seminar we will be solving the following problem. Recall that any circle that does not pass through the center of inversion is taken by the corresponding inversion of the real plane with respect to a circle into what? Into a circle. In other words, inversion can take circles into circles. And that is the idea behind the next problem. In the next problem, we'll be given two distinct non-concentric circles. Let's say we're given this circle and we're given, I don't know, let's say, and we're given this circle. Two circles that are not concentric. We will be looking for inversive magic that you are expected to generate in such a way that this magic will take both of these circles into two concentric circles. So we are looking for a way to generate from these two circles that are somehow concentric and they have one center. So the inversive magic that you're expected to generate should take two such circles that are not concentric into the circles that are concentric.